Ever use these authenticator apps with the changing codes? They are pretty useful for security, but have you ever wondered how they actually work? Let's find out. Meet Alice and Bob. Alice wants to send a message to Bob, but she needs to make sure Bob knows it's really her and not some imposter. They agree on a secret password, like banana. Alice includes the secret password in her message, and Bob uses it to confirm it's really her. Simple enough, right? But there is a problem. If someone steals the password, they can pretend to be Alice. Yikes. What if we change the password every time? Alice and Bob could keep a counter. The first password might be banana 0, the second banana 1, and so on. No, the password is different each time. But there is still a problem. The pattern is too obvious. If someone spots the sequence, they can easily guess future passwords. To mix things up, we need a hash function. But what the hell is a hash function? Hash functions are like magic blenders. They take any input and scramble it into a fixed size output. For example, SHA-1 is a hash function that produces a 160-bit output, which can be represented as 40 hexadecimal characters. Why are hash functions so awesome? If you put the same thing into the blender, you get the same result every time. Even if you change the input just a tiny bit, the output is completely different, it scrambles everything. It's super easy to put data into the blender, but looking at the output, it's almost impossible to figure out what you put in. Now, just sticking the secret password and the message counter together isn't enough. It leaves the system open to certain attacks. We need to use something called HMAC instead. Think of it as a special way to mix the hash function, the secret password, and the message counter. Okay, we've got this long scrambled hash, but typing that whole thing every time would be a nightmare. So we shorten it to a 6-digit code. Here is how. We grab a part of the HMAC output based on the last hexadecimal character. Then we convert it to base 10 and take the last 6 digits. This becomes our secret password. So that was HMAC-based one-time passwords. We are just one step away from the time-based version, which is what Authenticator apps use. The big difference? Instead of keeping track of a message counter, they use the current time to generate a message number. Every 30 seconds, the password needs to be changed, so the message number will be the number of 30-second intervals passed since January 1st, 1970. So here is the whole process. Alice calculates the message number based on the current time and uses that number along with the secret key to generate the HMAC, which is then reduced to 6 digits. She sends it to Bob, maybe with a rocket ship, because Bob has to do the same calculations in less than 30 seconds, and if the results match, boom, it's really Alice. One last thing. How do Alice and Bob share the secret key in the first place? QR codes. When you scan a QR code with your Authenticator app, it contains something like this. It's got a label and a randomly generated secret in a special format called base32. The app reads this info and sets everything up for you. That's how Authenticator apps work. Pretty cool, huh? Next time you use an Authenticator app, you will know the magic behind it. If you found this helpful, don't forget to like, share and subscribe.